Hi everyone, today we will talk about complete manifolds. In analysis, we say that a metric space is complete if every Cauchy sequence converges. We will take this as our definition in this lesson. Today we will be relying more than usual on topology and the theory of metric spaces. From now on, we will always assume that our Riemannian manifolds are connected. Otherwise, most of our theorems will not make sense. Remember that when we have a Riemannian manifold, the distance between 2 points is defined as the infimum of the lengths of curves connecting them. This definition turns our Riemannian manifold into a metric space. We will say that the Riemannian manifold is complete if every Cauchy sequence converges. In other words, for any sequence xi with the property that for any epsilon there is n such that for I and j bigger than n, the points xi and xj are at distance less than epsilon, there is a point x infinity such that the distance between xi and x infinity goes to 0 as I goes to infinity. There are very simple examples of Riemannian manifolds that are not complete. Take the interval -1, 1. If we take a sequence of real numbers that converges to -1, it is going to be a Cauchy sequence, but it does not converge to any point in the manifold. Something similar happens if we take any open set in Rn that is not Rn itself. It will not be a complete Riemannian manifold because there will be Cauchy sequences that converge to a point not on the manifold. Another interesting example of non-complete Riemannian manifold is the cone. We are not including the tip because if we did, it wouldn't be a smooth manifold. However, there are sequences of points that are Cauchy but cannot converge because they would converge to the tip. In this lesson, we will prove the Hopf-Rinow Theorem, which gives 4 equivalences to being complete. This theorem also states that under any of those conditions, the infimum in the definition of distance is actually a minimum. In other words, in a complete Riemannian manifold, for any 2 points, there is always a minimizing curve connecting them. Before we prove the Hopf-Rinow Theorem, we will state 2 theorems, which we will prove in later lessons. They show how in complete Riemannian manifolds, the curvature and topology are closely related. The first one is Bohnet-Meyer's theorem. It states that if we have a complete Riemannian manifold with Ricci curvature greater than a positive number c, then the manifold has diameter at most pi times the square root of n-1 over c and has finite fundamental group. The second one is Cartan-Hadamard theorem. It states that if M is a complete Riemannian manifold with non-positive sectional curvature, then for any point P, the exponential map is a covering map. This has powerful implications on the topology of M. Now we go back to the Hopf-Rinow theorem. The 4 equivalences are the following. For some point P in M, the exponential map at P is defined everywhere on the tangent space TPM. Before, we proved that it was always defined on a small neighborhood of 0. This equivalence is saying that exp P is defined everywhere. The second equivalence says that any geodesic can be extended indefinitely in both directions. The third one is that the manifold is complete, and the last one that closed and bounded subsets of the manifold are compact. The second condition is easily seen to fail in the examples we mentioned before. If you have an open set in Rn with the usual metric, there are straight lines that cannot be extended indefinitely, making the manifold incomplete. In the cone, the straight lines that go up to the tip of the cone cannot be extended any further, so the cone is not complete either. Now we prove the theorem. We will begin by showing that D implies C. If we want to show that M is complete, we need to take a Cauchy sequence and show that it converges. If a sequence is Cauchy, then it is bounded, meaning it is contained in a large ball. By hypothesis, that closed ball is compact, so the Cauchy sequence converges. Now we show that C implies B. This one is a little more difficult, but the idea is pretty standard. We will assume that the manifold is complete, and we'll show that any geodesic can be extended indefinitely in both directions. By the homogeneity property of geodesics, we can assume that gamma has speed 1 at all times. Let B be the set of numbers s bigger or equal to b such that the geodesic gamma can be extended to the interval as. Let B0 be the supremum of B. We want to show that B0 is infinity. In other words, that we can extend the geodesic forward for all times. Assume by contradiction that B0 is a finite number. Then we can define a geodesic gamma tilde on the interval a, B0. This is because by our choice of B0, for any epsilon we can define it on the interval a, B0 minus epsilon. These geodesics agree on their domain of definition because they agree on the interval AB, and if two geodesics agree on a non-trivial interval, then they have to agree for all times. Now let xi be the sequence gamma tilde of B0 minus 1 over I. Since gamma tilde has speed 1, the distance between xi and xj is at most 1 over I minus 1 over j, which goes to 0 as both I and j go to infinity. This means that the sequence xi is Cauchy, and by hypothesis, it converges to a limit point we call y. Now if we go back to the class on geodesics, we prove that y has a neighborhood and a positive epsilon, with the property that any unit speed geodesic in that neighborhood can be extended for time epsilon. For delta small enough, gamma tilde of B0 minus delta will be in that neighborhood, and therefore gamma tilde can be extended beyond time B0, contradicting its maximality. This proves that gamma can be extended all the way to plus infinity. With an analogous argument, we can also extend gamma backwards in time to minus infinity as well. This finishes the proof that C implies B. Now we show that B implies A. We assume that geodesics can be extended indefinitely and want to show that the exponential map at a point P is defined on the entire tangent space TPM. This is going to be very easy. Pick V in TPM. From the existence of geodesics, we know that gamma V is well defined for some small time minus epsilon epsilon. By hypothesis, gamma V is going to be defined for all times, in particular at time 1, which is what we need to define xp of V. Finally, we show that A implies D. This is by far the longest step. In order to do that, we first prove a couple of lemmas. Let P and Q be points in a Riemannian manifold. Assume that the ball of radius r around P is a normal ball, meaning that the exponential map is a chart. Also assume that Q is a distance more than r from P. Define f to be the distance from Q, and pick x0, a point where f attains its minimum in the compact ball of radius r over 2 around P. Then the distance from P to x0 is r over 2, and f of x0 is f of P minus r over 2. This means that x0 is at the boundary of the ball, and x0 is effectively closer to Q than P by r over 2. We first prove the second equality. By the triangle inequality, we know that f of P is at most the distance from P to x0 plus the distance from x0 to Q. The first one is at most r over 2, and the second one is f of x0. This shows one inequality. Now we assume by contradiction that the inequality is strict. In that case, f of x0 is greater than f of P minus r over 2 plus epsilon for some positive epsilon. Using that epsilon, take a curve alpha from P to Q with length less than f of P plus epsilon. It exists by the definition of distance. Then the length of alpha is also less than f of x0 plus r over 2. This curve has to exit this ball at some point we call y0. We now break alpha into two curves, alpha 1 and alpha 2, where alpha 1 is the portion from P to y0 and alpha 2 is the portion from y0 to Q. By definition of distance, f of y0 is less than the length of alpha 2, which is the length of alpha minus the length of alpha 1. The length of alpha was less than f of x0 plus r over 2, and the length of alpha 1 is at least r over 2. Therefore, f of y0 is strictly less than f of x0, which was assumed to be the minimum. This contradiction finishes the proof of the fact that f of x0 equals f of P minus r over 2. Now the other equality will be very easy. By the triangle inequality, we have that P and x0 are a distance at least f of P minus f of x0, which is r over 2. This finishes the proof of the lemma. Now we turn to the next one. The second lemma is actually part of the Hopf-Rinow Theorem. If we assume A, then for any Q in M, there is a minimizing geodesic from P to Q. Take a normal ball around P. If Q is in this normal ball, then we showed in the lesson about minimizing curves that the radial geodesic from P to Q is minimizing, so we can assume that Q is a distance at least r from P, meaning that we can use the previous lemma. let f be given by the distance from Q and x0 a point in the closed ball of radius r/2 where f attains its minimum. By the previous lemma, we know that x0 is a distance r/2 from P, so we can write it as gamma v of r/2 for some unit vector v in TPM. Remember that we denote by gamma v the geodesic with initial velocity v. Since we are assuming that the exponential map is defined on the entire tangent space TPM, the geodesic gamma v is defined for all time. We will show that this geodesic is minimizing from P to Q. This makes sense since x0 was chosen to be the point closest to Q, so if we start moving from P to x0 and keep going, we expect to be moving towards Q. Let L be the distance from P to Q. We want to show that gamma v of L is Q. This will finish the proof of the lemma because gamma v from time 0 to time L has length L. Let A be the set of times from 0 to L for which f of gamma v of t is L minus t. This means that the times in A are the ones when gamma v is traveling optimally from P to Q. We want to show that L is in A, so we assume not. Let T1 be the supremum of A and let P1 be gamma v of T1. Notice that A is the set where two continuous functions agree, so it is closed. In particular, T1 is in A. Also, I will ask you to check that if T is between 0 and T1, then T is in A. This is not super easy, but it's not hard either. You will need to use the triangle inequality a couple of times. Now take a small normal ball of radius delta around P1. By making delta small enough, we can assume that Q is not in that ball and we can apply again the previous lemma. Let x1 be a point in the closed ball of radius delta over 2 that minimizes f. We will show that x1 is a point in gamma v. For that purpose, let y1 be gamma v of t1 minus delta over 2. We now compute the distance from x1 to y1. By the triangle inequality, it is at least the distance from y1 to q minus the distance from x1 to q. This is f of gamma v of t1 minus delta over 2 minus f of x1. Since t1 minus delta over 2 is in A, the first term equals L minus t1 minus delta over 2, and by the previous lemma, f of x1 equals f of p1 minus delta over 2. Since p1 is gamma v of t1 and t1 is in A, some terms cancel and we simply get delta. On the other hand, we can construct a curve of length delta from y1 to x1. Simply travel along gamma v to p1 and then take the radial geodesic from p1 to x1. This curve has length delta, so it is minimizing. Now we have proven that minimizing curves are geodesics, and if two geodesics share a portion, then they are actually the same geodesic, so the curve that I drew in here is simply gamma v. This shows that x1 is gamma v of t1 plus delta over 2. Finally, again by the previous lemma, f of x1 is f of p1 minus delta over 2, which in turn is L minus t1 minus delta over 2. This shows that t1 plus delta over 2 is in A, contradicting the maximality of t1. This finishes the proof of the second lemma. Now we come back to the Hopf-Rinow theorem. We can now prove that A implies D. Take K a closed and bounded subset of M. Since it is bounded, it is contained in the ball of radius r around P for some large r. By the second lemma, when we take the exponential map in TPM, the ball of radius r around 0 is sent surjectively to the ball of radius r around P. By the Unraveled theorem, the closed ball of radius r around 0 in TPM is compact. Since the exponential map is continuous, its image is also compact. Then K is a closed subset of a compact set, so it is compact. This finishes the proof of the Hopf-Rinow theorem. And this is it for today. Next time we will talk about Jacobi fields, an important tool to connect curvature and topology. Hope to see you all there.